Okay, chapter 3.4, we have a lot of stuff thrown at us, so I broke it down into pieces. First thing we need to look at is the rational zero theorem. Alright, and all it says that if I have a polynomial function, so let's pretend like I have a generic function, f of x equals ax to the nth power plus bx, if I can write, to the n minus 1 power plus, cx to the n minus 2, etc., right? Plus dot, 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 plus, I'm eventually going to have some constant term by itself, right? Examples, if you need, if I need to write something actually out for you, would be 3x to the 5th power minus 4x squared plus 2, okay? That's a generic looking polynomial. It has, it can have many terms, and my leading coefficient is 3, and my constant terms are 2. So with the rational zero theorem, you're mainly looking for the leading coefficient and the constant term. That's what you want to deal with, the leading coefficient and the constant term. And what you're going to do is, the first thing you're going to do is list out factors of the constant term. So list out all the factors of the constant term. So list factors of the constant term. If I can write. And then you're going to also list the factors of the leading coefficient. So list factors of the leading coefficient. Okay? Now once you list these factors, you're going to do a quotient. Okay, so it's going to be the constant terms factors divided by the leading terms factors. And here's an example for us to work with. So the constant term is 5, right? So I have 5. Now what are the factors of 5? Well, plus or minus 1 plus or minus 5. What's positive 1 times positive 5? It's 5. What is negative 1 times negative 5? It's 5. These are factors, right? The leading coefficient is a 1. So the factors of 1 are plus and minus 1. Positive 1 times positive 1. Negative 1 times negative 1. You must list all of the factors, positive and negatives, and then you're going to divide them. And it's going to be the constant term divided by the leading coefficient. So positive 1 divided by, plus or minus 1 divided by plus or minus 1. So plus or minus 1 divided by plus or minus 1. What does that equal? Plus or minus 1. Good, that's the first one. What about plus or minus 5 divided by plus or minus 1? You gotta do all of them. What does that give me? Plus or minus 5. So the rational zero are giving you the possible zeros of your polynomial. They may not be the actual zeros. They may not work at all. So right now I'm saying 1, negative 1, 5, and negative 1 are possible zeros of this function. Possible zeros. Not necessarily true. They may all be zeros, they may all not be zeros. One of them could be a zero and the other 3 may not be, or etc. So the rational zero theorem says you take the factors of the constant term and the factors of the leading coefficient and you divide them. Okay? Constant term factors go on top first. The leading coefficient goes on the bottom. Constant term on top, leading coefficient on the bottom. Alright, the next piece we talk about in 3.4 is Descartes' rule of signs. Now, all this is basically telling me is how many possible positive real roots can this, yes, that's right. How many possible positive roots can this function have? And how many possible negative roots can this function have? A lot of words, right? So the first thing you're going to do is you're just looking for literally how many sign changes, right? So you go from minus to a minus. That's not a sign change. It's the same sign change. So there is no change here. So no change. And then guess what? You're at the minus and it goes to a plus. But I'm missing one, aren't I? Because there is a plus sign in front of that 3. He's positive. So when I go from positive to negative, I have a sign change here. And I have a sign change here. Which means I have 2 sign changes. So I have 2 sign changes. 2 sign changes. And the rule is the number of positives. So let me see if I can write this down. Number of positive one second. The number of positive real zeros is always going to be, let me make sure I get the wordage right, is always going to be the same as the number of sign changes or less than the number of sign changes by a positive even integer. So it's always going to be the same number of sign changes. So how many sign changes did I have in f of x? Well, I had 2. So the number of possible real roots can be 2, or is going to be less than the number of sign changes by an even integer. And an even integer would be like 2. So 2 minus 2 is 0. So I can either have 2 positive real roots or I can have 0 positive real roots. Does that make sense? Okay. Now let's how about the negatives? The negatives, well, first of all, you got to change this around. Do some erasing. Okay, to find the negative real roots using Descartes' rule of sign, you need to do f of negative x. F of negative x. I've already seen x, put a negative x, right? So 3 times negative x to the 4th minus 2 times negative x to the 3rd minus 8 times negative x plus 5. So f of negative x is equal to 3x to the 4th, right? Because negative x to the 4th is the same as saying x to the 4th. Well, negative x to the 3rd is like saying the negative stays there, right? I'm going to end up keeping the negative. So this can become plus 2x to the 3rd power. And negative negative makes that again plus 8x plus 5. Now, you're going to do the same thing. You're looking for the number of sign changes. So the number of sign changes, let me change the color. So this is a positive. Positive, positive, no sign change. Positive, positive, no sign change. And still no sign change. So the number of negative real roots, if I get this thing to right, of negative real roots you're going to follow the same rules as it was with the positive, so it's always going to be the same number of sign changes, or it's going to be less than the number of sign changes by an even integer. Well, here I had 0 sign changes, right? Therefore, I have 0 negative real roots. Let's pretend like I had 4 sign changes. Then I can have 4 real roots, or I can have 2 real roots, or I can have 0 real roots, right? Let's make sure we understand what does it mean to be less than an even integer. What if I had 1 sign change? Just 1. Well, to subtract an even integer, make it negative, right? So the rule is you just stay with the 1. 1 is the only option at that point. And as you do more problems with the homework, you'll understand what I'm talking about. You'll get more practice. All right, so we went through the rational zero theorem, and we went to Descartes' rule of signs. Now, the last one is the linear factorization theorem. For a long time, we have always talked about finding the zeros or the x-intercepts or the roots of a polynomial, right? In reality, this is how it's written. F of x is written in the following form. F of x equals a, where a is a constant, times parentheses x minus c, times parentheses x minus 2, and etc. It goes on forever. Think back to when you're factoring, and you end up with, and you end up with something like f of x equals, 3x minus 2, can I do this? Times like x plus 5. That's horrible. But the whole point is, do you see there's a product between the factors? There's a product going on. That's the same thing that's written here. Okay, so now what we're doing is we're learning how to work backwards. Learning how to work backwards. They give you certain clues about what your polynomial looks like, and you just got to fill it in. So let's read this. I want red. I'll take green. Okay. So n equals 3. Well, n is the degree of my polynomial, right? So I know I have a degree of 3, which means how many of these x minus c should appear? If I have a degree of 3, I must have 3 roots, right? That's how it works. Therefore, I know I'm starting off with 3 of them. So I'm going to have f of x, f of x equals, well, a, some constant. Now it's going to be x minus something times x minus something times x minus something else, right? These somethings are my zeros. So they tell me 2 is a 0. If you think back to synthetic division, I always divided by x minus c, where c was the 0, right? Well, here it is, 2. I take that back. C is not your 0. So ignore that last sentence. Just remember x minus c is the form I need to be in. All right, so c is a 0. So c's represent the zeros. I really don't know what's going on here with this pen. It starts off well, and then it just dies on me. So c's represent the zeros. So 2 is a 0, right? It says 2 and 2 minus 3i are 0. So 2 is a 0, which means that's going to be x minus 2. Great. And then it says 2 minus 3i is also a 0. So this is, let's make some room. So this is x minus 2 minus 3i. And I'm using parentheses because of that minus minus. You have to make sure you distribute it. So I'll do that in the next step. And then the last factor is x minus. Now the rule is, if an imaginary number is a 0, its conjugate, I really don't know why I try writing. Oh, there we go. Nope, there we go. Oh, it's a perfect key. Its conjugate, and that's why, it's sloppy. Its conjugate is also a 0. And the conjugate just means change the sign in front of the imaginary part. So 2 minus 3i and 2 plus 3i are conjugates. We've done this earlier when we talked about dividing imaginary numbers. You divide it top and bottom by the conjugate. Well, the conjugate of 2 minus 3i is 2 plus 3i. So again, I need to use the parentheses. 2 plus 3i. Okay? So let's clean this up. So I have f of x. Oh, it's horrible looking. Okay, so I have f of x equals, still a. I don't know what that constant is out front right yet. times x minus 2, 2 times x minus 2 plus 3i. Gosh. And x minus 2 minus 3i. I hope you're listening as well as watching because it's very difficult with this pen. Okay, now how do you find the a term? They gave me some more information. They said f of 1 is equal to negative 10. F of 1. Everywhere I see an x, I'm going to put a 1. That's what it means. F of 1 equals negative 10. So this right here, I normally would write it as f of 1, right? But since I know it's negative 10, I'm going to write it as negative 10. I'm going to end up running out of room. So I have negative 10 equals, well, the a is still there. Now, what is 1 minus 2? It's negative 1. You basically, everywhere you see an x, put a 1. What is 1 minus 2 again? It's negative 1, but now it's plus 3i. And again, 1 minus 2 is negative 1 minus 3i. And basically it becomes a game of solving for x. So negative 1 plus 3i times negative 1 minus 3i is going to come out to be, I believe it's positive 10. So now this becomes out, now I get an equation that says negative 10 equals a times negative 1 times positive 10. Oh gosh, there we go. And if you don't believe me, I expect you to be working that out. FOIL the last two pieces together. So negative 1 times negative 1, that's 1. The middle terms disappear, and this will give me a negative I squared. Negative 9i squared makes it positive 9. I get to 10, which means now I need to work up. So I have negative 10 equals negative 10 a. Oh gosh. Which means if I solve for a is just equal to 1. So the answer to here would be, instead of writing, I'm running out of room, so I'm going to have to write over it. I'm going to erase basically. So my final answer, instead of having the a, the leading coefficient is a 1. And then I have x minus 2. X minus, and you can leave it in parentheses like this, the following factors, x minus 2 minus 3i, and x minus 2 plus 3i. Okay, so this is what they're looking for. And I know I ran out of room, so it got a little messy there, so you have to forgive me. But there's your final answer. So you just created a function based off of their clues, and you had to work backwards, basically. Okay, so let me know if you have any questions. 3.4 covers a lot of new material. And basically the takeaway is, if you wanted to know how many possible zeros you had, you can use the rational zero theorem as well as Descartes' rule of signs. Okay? To do the rational zero theorem, you need to be listing the factors of the constant term divided by the factors of the leading coefficient. Descartes' rule of signs says, well, the positive real roots are going to be how many sign changes are in f of x. So you're looking for sign changes in f of x, or the positive real roots. And then for the negative real roots, you're looking for the sign changes in f of negative x.